In this narrated PowerPoint, we're going to walk through some of the algebraic expressions for the means and variances of sums of random variables. This material is in section 4 of this week's reader. We did a little preview of this in section 3 of the reader with two random variables, x and y, but now we're going to need to work with random variables. So when we talk about the sum of several random variables, we'll denote each random variable by an x, and we'll use subscripts x sub 1, x sub 2, x sub 3, and so on up to the last one, x sub n. We'll write that in a compact summation notation as the sum, I going from 1 to n, of a generic x sub I. Generalizing on our results with the sum of two random variables, we're going to have the fact that it is always true that the expected value of a sum of random variables is the sum of their expected values, or in compact notation, the expected value of the sum I equal 1 to n x sub I is equal to the sum I going from 1 to n of the expected values e of x sub I. And in the important special case we're going to work with, where we'll have simple random samples of size n, we'll be assuming that our simple random samples are from a homogeneous population. Now, what that means is that each observation gets its own random variable x sub I, but if it's a homogeneous population, all of the x sub i's will have the same probability distribution, and in particular, they'll have the same mean. So we'll be talking about the mean of the sum of n identically distributed random variables for our homogeneous population. And since they're all the same, we're going to denote the mean of each x sub I by simply e of x without any subscript. So that formula, the sum has an expected value that is the sum of the expected values of each x sub I, simplifies to n times this expected value of x. So the mean of the sum when the x sub I all have the same mean is simply n times mu. Now, especially if you're tired, this may seem like a lot of algebraic sleight of hand. So let's put these formulas to work in a simple teaching example. So we're going to think about the total weight of 25 airplane passengers. This is from the Moore and McCabe and Craig textbook, the cousin of our textbook. It's actually one of their examples, so I want to give them credit. The details are in our reader in section 4. So suppose we know that the mean weight of airline passengers on short commuter flights in the summer is 190 pounds, including their baggage. Then the mean of the total weight of the 25 passengers by the formulas we've worked out is simply 25 times 190, or 4750 pounds. This is a number that might be of interest to us if we needed to do fuel calculations for a small plane based on the weight of the anticipated passengers. We're also going to need information about the variance of the sum of independent random variables. Remember from section 3 in the reader and our previous work, the relationships happen on the variance scale. So we're going to have to do our calculations on the variance scale and then take square roots to get standard deviations. Now, the results are a bit more complex for variances and standard deviations than for means, so we're just going to state them. And in particular, we need a big qualification here. For independent random variables x and y, the variance of the sum is the sum of the variances. Or in notation, the variance of the quantity x plus y is the variance of x plus the variance of y. So that's another reason for us that simple random samples or randomized experiments are really important, because with simple random samples we do know that the observations are independent, and so we'll have the variance of the sum equal to the sum of the variances of the x sub i's. And then for a homogeneous population, this sum of the variances further simplifies to simply n times the variance of x, or in the common notation for population variances, n times sigma squared. So let's go back to our airplane passengers weight problem. Again, credit to Moore, McCabe, and Craig, example 5.29. I use this text for my summer course, Public Health 141, but Moore, McCabe, and Craig are actually a 2-semester book, which is why we're using the Baldi and Moore for W142. But suppose we know that the standard deviation of the weight of our passengers, again, we're restricting ourselves to short commuter flights in the summer. Suppose we know this standard deviation is 35 pounds, again including their baggage. So if we ask what is the standard deviation of the total weight of the 25 passengers, then we first have to work out the variance of the total weight. So the variance of the total weight is 25 times 35 squared. Remember, we have to square the standard deviation to get a variance, or about 30,625 pounds squared. And then to think about this, we'll take the square root to get the standard deviation of the total weight. So the square root of 30,625 gives us a standard deviation of the total weight of about 175 pounds. We'll come back to this example after we do some more work with means and variances, and then shapes of sampling distribution.